Because your f of ax plus b just means that in your function it has a linear transformation in it. So if I had to give you a couple examples, it would be something like, it's just saying if you had ax plus b to the power of n represents that. This is e to the power of ax plus b. This is sine of ax plus b. They're just asking you, can you antiderive those functions? That's what that dot point is representing, which is all of, you can find those in different exercises of chapter 11, but that's what that dot point is talking about. And today's session, I'm specifically looking at this one. Okay, so I'm looking at your polynomial, because it comes up literally every year since 2009 for exam 1. And it's literally so predictable since 2009. I was just telling my students every year, I said, it's going to come up. It's going to come up. And it's funny because I tell them that day in, day out. And then when it comes to this act, they still couldn't do it. And it's like, why? I told you before. I said, it's not going to be in your formula sheet. Do it. It's the one exercise that I know is going to be there. And they still didn't do it. So I think I'm going to say it again to you guys this year. Say the exact same thing I'm going to say. And I think it may come up in 2016 just because they're changing the course. It might not be. Okay? Okay, so these are the two rules that aren't going to be on your formula sheet. That I want you to either memorize or at least know how to do. Okay, so this is now x to the power of n, and you're doing a transformation of ax plus b. That's what it really is. The difference is there's two scenarios. The power that you have, x to the power of n, that power, as long as it doesn't equal to -1, it follows the first formula. Okay, so the first formula is exactly the same way you've been doing your antidiff. Okay, so if you had the last lesson I did with you, it's exactly the same thing as ax to the power of n, okay? There's no difference in that formula. If you remember that formula, it was x to the power of n plus 1 over n plus 1 multiplied to a. True? Well, it's the same thing. If you look at it, it's exactly the same concept. You're also doing exactly the same thing here. That's your r plus 1, that's your r plus 1, that's your n plus 1, that's your n plus 1. Okay? So, therefore, if you have anything that is not -1, so it could be, 2x plus 3 to the power of 4. It could be 2x plus 3 to the power of half. Okay, they all follow the same formula. And you would use that. Now the question is, well, why doesn't it apply for r equals -1? And if you think and you remember, 1 over ax plus b is almost similar to just saying 1 on x, because that means a is 1 and b is 0. Okay, so that's the same thing as just writing 1 on x. Now if you remember your derivative rules, derivative of what gives you 1 on x? Anyone know? Log. Okay, so that's why we know that that means the antidiff of 1 on x has to give you a log. That's the only one that's different to this. So that's why when it comes to the antidiff of 1 over where r is the power is -1, you get this. Now I'm going to explain in the next few slides why it is the modulus of ax plus b. Okay, but these are your two formulas, unless they've changed the formula sheet, which I should check actually. Previous years, the formula sheet will not have these two. And therefore in exam 1, a lot of students won't be able to do this question because, they don't have a formula sheet to follow. They do a random guess and whatnot. They normally forget the factor of a is what happens because of that dilation factor there. Okay, when you're doing the antidiff and you forget the formula, you don't know how to use it, you normally forget that a value. Okay, so let's see how we're going to use this formula here. So I've given you these two formulas. I said they apply to a polynomial where the transformation is linear. Okay, so let's have a look. If I gave you, as just a note on the bottom if you want listening, it is not on your formula sheet and it's been very consistent since 2009. And you'll see in the last slide of this PowerPoint, I've got a whole list to show you how consistent it's been. Okay, and what kind of questions they do. Now let's have a look. The logic to this, if you wanted to know logic, you can skip through this if you want. I'm just going to quickly show you. What I try to show you is how you normally derive the formula using chain rule is you find the derivative of the inside and you derive the outside. Yeah? which is why when you go backwards, and I'll split it up so you can see, I've color coded so you can see here, you normally say drop the power down, so that's your 3. This is the derivative of the inside. Oh, sorry, that's the power. Whoops. There you go. That's your derivative of the inside, so this is A dash. Okay, this is dropping the power down and finding the derivative of your x to the power of n. That's what you're really doing there. Yeah, so n minus 1 is this one, and then bringing n minus 1 down, that's there. Yeah? Now, because of that, if you're going backwards, it makes sense why you would then, if that's the derivative and you simplify, it gives you the last line. This is technically the steps that you're focusing on. You times 3 times 3, and what does this 3 represent? It was your a value, which is that, and that is the result of your power. 3 came from the power. Yeah, you dropped the 3 down, that's what you did. So this is your n plus 1. If you want to remove that, if you want to go backwards, instead of times, you would divide. Because if you derive, when you derive, you go forward. When you antiderive, you go backwards. So if you derived, you times everything, then when you antidiff, you divide. Which makes sense why the rule, this is what you're saying here. You're just saying divide r plus 1, which is your 3, and then divide a, which is the derivative of the inside. And that's why you're saying divide that. That's what you're doing. You're actually just saying, if I rubbed everything off, all I'm just saying is if you want to go backwards, add 1 to this, divide 3, divide 3. The question is, where's that 3 coming from? That came from the original power, which is n plus 1, because you're minus 1, so you're n plus 1. And where did this 3 come from? It came from the derivative of the coefficient of your linear, which is here. And that's why it's a divided by a. And that's what this is really saying. It says divide a and divide your power. That's all it's doing. So you're just doing the inverse. And then same thing here, add the power back because you subtracted 1 initially. Okay, so you're just doing the reverse of your normal power rule. Okay, so if you had to forget, that's the logic for it, why the formula works. So if I gave you this and I asked you to find the antidiff, I'm just showing you what they're doing. So in that step, I'm just translating this step over here. If you want to remove it, so you're dividing by the coefficient, which is 3. You're dividing it by the power, which is 2 plus 1. That's only the power. And from 2 to get back, 2 plus 1. Okay, so that's the logic for it. But again, you don't need to know that. If you just want to know how to use it, memorize that formula. Okay. Now, let's go to r negative 1. Why is it that you've got a modulus, meaning you can have a negative and a positive? The logic to this is very simple. If I gave you a derivative of log e of 3x, you would tell me that you would using chain rule, let a equal to the 3x. I'm just saying replace 3x with a, and you end up with f of a equals log e of a, and I ask you what's the derivative, you'd say the derivative is 1 on x, if you follow those steps. Okay, so if you found the derivative of the inside, that gives you 3 multiplied to the derivative of the outside. It's 1 over 3x, and you can see the 3's cancel out. It's 1 on x. Now that's normal. You're like, okay, I understood that, sir. I knew that in chapter 9. I'm like, yeah, cool. And then if you do the same thing for the negative of 3x, is what you find is the same thing happens again. You find the derivative of the inside, which is negative 3, times by the derivative of the outside, which is 1 on negative 3x. Okay, and if you multiply those two, again, same thing, you get 1 on x. So that means when you find the antidiff of 1 on x, you potentially can have a plus or minus 3x, which is why they call it modulus. That's where the logic comes from. Okay, and so there we go. So I'm just proving that, if you found the antidiff of each side, it gives you a plus and minus. That's why it's a modulus. Okay. And again, you can always go back and have a look at this PowerPoint slide to make sense out of it, or watch the video again. But here we go. So let's do a couple of examples just to get you the feel of how to use these rules, because today's session was literally focusing on those 2 rules. And then I'll show you how many questions in every single year your past exams come up with the same one, and you're just using this rule or the other one. That's it. There's only one or the other. Okay, it's 2 marks out of your 40 marks, which is great. It's like, what, 1 out of 20. It's something worthwhile doing. Yeah. So here we go. So you got your 3x plus 6. Again, I said any power that is not equal to negative 1. This is not equal to negative 1. Yes, Corinne? Oh, this formula exactly? Oh, then yeah, I'll probably go with it's less likely to come up then, because every previous years that didn't have it. Previous years you don't have this formula. That's why I always knew it came up. Then it might actually not come up this year then. Might be worthwhile learning anyway, yeah? But yeah, every other year it always had it. Didn't have it, yeah. Okay, so you got your formula. You're going to use the formula pretty much the same thing. A, which is 3. And then you've got the power, -1, -half plus 1, and with a -half plus 1. So I'm just using the formulas there. So it was a very straightforward formula. It's just that when you have that linear factor to it, it made a lot of difference to a lot of students, because a lot of students can do this. That's easy. But as soon as I put in a linear factor to it, in previous years, a lot of students would find that difficult to do. And that was exactly the same technique that you would normally do, it's just you have to pay attention to the dilation factor. Okay? Now, if we have to go through the steps, same thing, I'm just going to multiply. That's -half plus 1 is half, 3 times half is 3 on 2, and we all simplify it down and it gets you 2/3 rid of 3x plus 6. Now, don't forget, it's an indefinite integral, so it has no boundaries right now. It's not from -1 to 1 or 3 to whatever it is, so that's why you always have to have the plus c. Okay? Now, same thing with the next one. I know the difference here is that it's 5 minus 2x, and if it did come up in previous years from 2009 to 2015, they normally give you the second one. The reason why they give you that one is because there's that -2x, and that actually tells you that a is a -2, and a lot of kids forget that, and they'd write just 1 on 2, 4 plus 1, and they follow the formula, and they just write 5 minus 2x to the power of 4 plus 1, is how they would have done it. And the mistake is not noticing that the coefficient of x is currently -2. So that means this should have been a -2. Okay, so that came up in, I'll show you later with the type of questions you get. So that's the only thing that you'd have to pay attention to this question. It's that one. Okay, because again, like I said, when it comes to that linear transformation in your polynomial, a lot of students forget that dilation factor and how it affects it. Okay, so that negative, if you've done it correctly, then the answer is pretty straightforward. Sub in the formulas and you get -1 on 10, 5 minus 2x. Okay. Now, if we now move on to, I'm going to skip these ones because the answers are all the same. Oh, actually, except for this one. Just in case you didn't know how to do these kind of problems, when you get a fraction like this, especially in methods, it's not specialist, so it doesn't ever get that difficult to do. If you ever get those kind of fractions, whether in your multiple choice section, like if you had x plus 1 and x plus 2, and they asked you to find the asymptotes and whatnot, list the equations, my first step to tell you or what to do is to go by that. And that's just your polynomial division. You literally write what you see. It says x divided by x plus 1. So you're really just saying how many x plus 1s fit into x. In my case, 1 times the x gives you the x, and 1 times the 1 gives you the plus 1. So find the subtraction. That gives you 1 whole. So that's 1 whole, because it has 1 whole here. So that's 1 whole. And remainder of -1, so -1 on x plus 1. Okay, if you're wondering why that works, it's exactly the same thing as saying 3 over 2. See, 3 over 2, what you would have told me is you would have said how many 2's fit in 3? I'd say once, you do once, 1 times 2, you find the subtraction, you get a remainder of 1. Now, you know 3 on 2 is the same thing as saying 1 whole with a remainder of 1 over what you were dividing by, which is 2. That's why 3 over 2 is the same thing as 1.5. Yeah, so same thing. So I'm doing exactly the same thing here. I'm just saying how many times it goes in, at times I found my remainder, so it goes in once whole, remainder of -1, over what you were dividing by, which is x plus 2. Exactly the same way you would have done for half. Okay, so if you can do 3 on 2, you can do polynomials with division as well. It's the same thing. Okay? So once you do the polynomial division, why do you do that? Is because then you can split up the integral. So you can now say that's 1 minus 1 on x plus 1. And the nice thing is you can write that using the properties. Split it up into integral of 1 and integral of 1 on x plus 1. This one we know. This is pretty much your log 1. Okay, this is to the power of -1. Yeah. So if you look on the right hand side, this is now like saying x plus 1 to the power of -1, and that follows the second rule. Okay, so that's the only thing that I thought might have been tricky. Other than that, everything else follows exactly the same way you've been doing. Okay, now having said that, I'm going to show you your exam questions. This is another formula that you have to learn, exponential. But I want to go to the past exam questions, and we'll go back to the slide. This is your 2009 to 2014, and it's exactly the same questions over and over. And I want you to analyze each one. You see, it's the same one over and over, and it's 2 marks, 2 marks, 2 marks, except for one of them was 3 marks, because it has a definite integral. But if you have a look, 1 minus 2x, what was tricky? Again, same thing, -2. It's a log one, because it's the power of -1. So they know that a lot of students will forget that it could be a modulus. Comes up, it's 2 marks, very straightforward. If you knew the formula, bam, we've got the answer straight away. Okay. Same thing with the next one. Notice again, negative, because they're doing the same thing over and over. They know students forget that coefficient. They're doing it on purpose. Instead of putting the 2 to make it obvious, they'll put now -x, so it's less obvious. But it's the same thing. It's always, they're trying to test how well you understand how to use the rule. And it's the one exercise, 11C. Okay? Same thing with this one. If you have a look, it's all logs, by the way. This is like 9, 10, 2011, 2009, 2010, 2011. Same thing. 1 over 3x minus 4. Again, that's a log one. And log has that modulus, whether kids remember it's a modulus or not. But it's 1 mark. So I think maybe by then they would have figured out that students know that this is coming up or so. Okay? And then they vary it in 2012, which makes sense because they've been doing it log, log, log. Then by 2012, they went, all right, let's play around. Let's do the other one now. Let's say it's not -1 anymore. And now it's -3. But it's the same thing. You see, and that was 2 marks. And then they follow on to 2013, same thing again. They wrote it, it looks different, but it's exactly the same thing. This is now 1 on 4 minus 2x. And again, that negative. See, they're purposely chucking those negatives. It's a very common thing to come up. You know, like when you get an easy question, like find the range, find the domain, it usually has a negative as a coefficient because students forget that. And if you have a look at the last one, same thing. This looks like, that goes back to logs again, but this time they give you a definite integral and a log e of b. They make it look crazy, but really, you know, it's a modulus of this again, and you'll get your answer between 4 and 5, and you'll know what the answer should be. You can figure that out. Okay, so it's all the same. All of that was going back to 11C, 2 formulas, but apparently now it's on your formula sheet, so it might be easier. But previously you didn't have a formula, so you can see why that's hard. Now your questioning is 2015 going to be different? And I'll show you 2015 is exactly the same. Okay, same thing. Since 2009, same thing, 2 marks. And yes, that looks different, but really this is just saying that's 1 on x to the power of half, which is exactly the same thing as it's not -1. Same drill over and over. So I thought if it's not on your formula sheet, it'll probably more likely to be on your exam this year again. Okay, but if it's on your formula sheet, I'm probably going to say less likely to now, just because it's been doing it since 2009 and they're changing the course, so maybe not. But hey, it's worthwhile doing because there's only 1 exercise, 2 formulas, and it's been consistent for that many years. You probably should learn it. You know, there should be somewhere, maybe in your multiple choice section or something. It's still worthwhile to know. That's what I want you to take out of this session. Okay. So every year I say the same things, but I think students just don't believe me or something. I don't know. I've shown that everything I could. It comes up every single year. Maybe not 2016. Okay, because prior to 2009, yes, it didn't come up as often. Prior to 2009. If it was antidiff, it normally was the last few questions, and it's an application question or area between curves, so you don't get it something like this. So since 2009, that's what they did. So maybe if I had to put a dollar on it, I'd probably say 2016 won't have it. That's my guess. Just because they changed the course, and if it's on the formula sheet, why would you make it that easy? It's not going to be there. Okay? Anyways, I might be wrong. I said $1, okay? Don't quote me on that. Actually, it's recorded on the YouTube thing, so I might actually get sued for this. No, you know what? Scrap the $1 thing. It might come up. I have no idea, okay? All right. Now, having said that, so what I really want to emphasize in that session was those two first formulas, the log, so when r equals -1 and the power doesn't equal -1, that's what I wanted you to definitely know. And in terms of your exponential formula, to me, this is pretty straightforward. The reason why it's so easy to do is because if you can derive it, it makes sense to go backwards. So if you derive e to the power 3x, you would have said derive the inside, that's 3. So if you want to remove it, divide 3. And that's literally the only thing they did there. They just said divide k. That's all they did. Okay, so that's why this formula is really easy. If you understood the concept, what I was saying at the start, it's just the reverse of your derivative. That's where all these formulas are coming from. They're just the reverse of your derivative. So you don't have to memorize them, because if you understood it, you can work it out. You can derive it first and then go backwards. Okay. In this question here, so examples 1 and 2, I think are pretty straightforward. I think I just wanted 3 for you guys to do, where they give you the derivative and they say it passes through a curve, find the equation of the curve. That's relating now back to chapter 9 and chapter 10. Okay, but other than that, everything else is pretty straightforward. So today's session, very simple, 2 formulas, and I want you to definitely know that. Okay, whether I want it to be sort of like an inside out. So if you know how to derive 3x squared, I want it to be like that. So if it comes up, at least you know it. And if it doesn't come up, well, it doesn't hurt you. Okay, but I do want you to know it as if it is something very natural for you to do, because it's likely, in the past, it was very likely to come up. That's why. Okay. And that's it for my session today. It's just, I thought I'd keep it easy. Next session, I'll talk about areas between curves and fundamental theorem of calculus. But that's where we'll stop for today. All right. Any questions? No? All right, I'm going to end this video. If I can just do this. And I heard that you have a special sack, so maybe you guys want to study that too.